Well, anyway, after this short technical glitch, sorry about that. We have checked beforehand, but you know how it goes. Let me welcome you all to the 7th edition of the Hope Workshop. I'm very happy to see you here, and I think we'll just jump straight into the talk. So this is a preview of a tutorial on polarized L calculi. So like a lot of work that's presented at Hope, it's work in progress, although not on the technical side, but on the formulation, I suppose, in a way that more people could get interested and learn more about the L calculi. So the floor is yours, Gabriel.
Thank you. So yes, it's you'll be used as guinea pigs for my attempt to explain this stuff to normal people, which is a terrible mistake because you're not representative of normal people. You know, many of you in the room know more about some of the things I will be talking about than I do, and so yeah, tricky business. I try to do a job of it. So I'm Gabriel, and I learned about polarized L calculi, which I will define shortly through Guillaume, who worked on it during his PhD thesis, and ever since, I would say. Xavier Montillet is a PhD student of Guillaume, and he has a weird obsession for the rewriting properties of untyped version of the system. So he's kind of the rewriting guy. Etienne is a postdoc in the same place they work, which is in Nantes, a lovely city. And he is interested in classical logic with dependent types and call by need. So also quite impressive specialization, I would say. And Kenji, who is in Paris, so close to where I am, is more of a category theory person. And of course, I'm the least knowledgeable of this bunch of people, and so they chose me to give the talk. So first, what do we call L? L is a short name for, I'm not sure where I should stay to avoid the glitches in the sound. For the polarized versions of the lambda mu mu tilde abstract machine calculi. So you can see why we need a better name than just explaining what it is. And the claim, first I had modest claim in my slide because some people claim more about L than this, but I try to just claim, is it's a good syntax to talk about classical computation, by which you can think of classical logic and computation or control operators. Okay? Mixed polarity equivalences, by which I mean equalities in languages where you have positive and negative types. For example, disjoint sums and functions, which is a topic that I studied quite a bit. Effects, so you know more about effects than I do, I won't define it. And purity, and nobody knows what that is. A kind of shorthand, I'm not sure, is Paul in the room? No? No? Wow. So a short simplification would be say that it's a good syntax, and for the semantics, think of call by push value. So many people would get angry at this statement, but I'm a generally calm person. And one way to think of it is when we talk about the notational semantics, it's not always the case, but most of the case we talk about a semantics where two programs that are equivalent by reduction are sent to the same mathematical object. So when we do not observe reduction in the semantics. So in a sense, the semantics we define, they talk about the values of a calculus, what you get when you are done computing. So the fact that two systems have the same values in this sense does not mean that the syntax are interchangeable, or they are not, that there are not phenomena that you can observe in different ways or different phenomena in the two systems. So it doesn't mean that it's the same thing as call by push value, although, yeah. And related works. So I said call by push value, so the models are related, and the syntax is worse, the syntax of call by push value. And there is also, there are many related works, of course. Mu mu tilde is a rich field, with many people work on it. as a kind of family of systems, but these are systems outside this family. Noam Zeinberger's PhD thesis that studied, so his work has a direct relation to focusing, whereas for Ellis it's a bit more of a, in a sense, after the fact realization, and emphasizes the syntax much less. So El talked more about syntax. So first I have to start with the basics, which are mu tilde. Do we have a poll down in the other poll? Is the other poll in the room? Or Zena? No, it's okay. I have to check how many of the authors of work I'm talking about will be around. So I assume that many of you are familiar, or will be shortly, with this style of abstract machines, so which are a way to implement the lambda calculus by saying, well, okay, we have the term, and we have a kind of stack or context, and we reduce pairs of that. So you can think of it as the context term decomposition given a first-class status. So if I have an application, one way to compute with that is to just push the argument on the stack, on the application stack, and continue reducing the term. And then eventually I will reach a lambda, and then I look at my stack, I hope to get an argument, and I do a beta reduction. Okay? And if you take such if you take a term, you put it against a special symbol that means the end of the stack, you reduce using these rules, and you get something that is you get the same result as head called binary reduction. Okay, so I hope that this is familiar. Okay, this is the syntax. Configuration of my abstract machine is a pair of a term and a context. A term is a variable, an application, or an abstraction, and the context is either this, what I said, end of stack symbol, or an application stack. Please feel free to interrupt me at any time with questions, okay? The goal is to get you understanding until the point where I stop my talk, which doesn't need to be the end. Feel free to interrupt. So, one way to introduce mu, I'm kind of, beta testing ways to explain the material. So it's helpful to get feedback if you don't like it. Is to say, well, if you look at this reduction rule, you can think of it as a property of application, but also as a definition, okay? TU, I can define it by saying TU is the term that when I put it against a stack that is E, reduces to T bar U cos E, okay? So it's a kind of a definition by how it behaves, and I can capture that by adding an operator to my system to mean exactly this. I introduce a primitive syntax, mu alpha, that means, so mu alpha, and then I expect a configuration. This is the term that when put against a stack alpha, reduces to this configuration, okay? So then I can say, okay, in the general case, mu alpha dot a configuration, by the definition I gave, I want to have this reduction rule. If you put me against E, I reduce this to C, where alpha is replaced by E, okay? And then you can define the application as syntactic figure for this new mu operator, okay? Pretty simple. And so it, yes. And then you can detroduce lambda by saying, okay, if you look at lambda, this reduction rule for lambda, you can think of it kind of in the same style, okay? Lambda xt is the term that when put against this reduces to this. But here I'm not handling the stack in a parametric way, I'm pattern matching on it, and I'm saying, I want my stack to be of the form mu.e. So it's this definition by what I do against a context, but with pattern matching added to the mix. So I can add primitive syntax for that, against. So this is the term that when put against a stack which has this shape, reduces to C. Yes?
So you keep saying the term. I can see it's a term.
Yes.
Is it going to be the only term that has this property?
No, there are other terms that are equivalent to this. Okay, a term. And so I have this reduction rule in the general case where I reduce at the same time U for X and E for alpha. Okay, pretty simple. And then the lambda xt form can again be introduced as a syntactic figure to say, well, I'm the term that when put against this stack reduces to this. And maybe you can take a minute to think about what this means in terms of programmer terms. The idea is, okay, when we write lambda, we give a name to the parameter. And here, you can think of it as a sort of a continuation style. I'm giving a name to the parameter, and also to what will be done with the result of computing the body of the function. Okay? So I'm saying, well, if the parameter is x, and what I want to do later is alpha, then I will compute t and send it to alpha. Okay? A bit informal intuition. And with this idea, so I kind of remove the lambda from my system. So you just have here, you have just in mu. Okay? The syntax I have is this one. And I can add more stuff following the same recipe, okay? So this is the elimination of pairs, the ones that are eliminated by pattern matching and not projection, okay? Let x1 t, so I mean, of course you know of this construction in programming languages. You can, in your abstract machine, make them reduce in this way, yes?
Can you say something about binding in third form?
This one?
Yes.
Both this variable and this covariable are bound in C. Yes, as in the examples here, x is used in T and alpha is used here. But of course here, alpha cannot occur in T because it wouldn't make sense. So I can use the same recipe. I can say, well, okay, this looks like a reduction rule for let. So let x, so and so on forth. It is the term that when put against the stack alpha reduces to this person, and here let equals whole in blah blah blah. I can rewrite it in my more mu style as mu x1 x2 and then the rest.
That's not a mu, that's a mu with a tilde.
Yeah, okay, let's leave it here. When I'm on the left, I write mu. When I'm on the right, I write mu tilde, just because. Yeah, but it's also mu. So I just introduced pair just for you. And then you may notice that there is a hole in my figure. And so why would we have a hole in a figure that is obviously about being nice and symmetric? So let's think of something to put here. And so let's have a mu. But so here I'm saying I have a mu that say, well, if you put me against the context alpha, I will do this. And here I'm on the right, so you need a mu that say, if you put me against the term x, I will do this. So you get a mu, and because we are on the right, you write sigma. But it could be mu bar or just mu. Actually, in this grammar, there is no ambiguity between the left and the right. And you cannot swap them, so mu would also be fine.
I see, so that's for let, u bar. U bar x.
Yeah, you can think of it of a let without the body part. So here in this example, indeed, the let x1 became mu x1. Thank you. Okay, so and then you get obvious elimination rules, reduction rules, because each time we have, on one side we have something that looks like a constructor, and on the other we have something that looks like pattern matching, so they match and they meet and they're happy. Yes?
Wouldn't you have an ambiguity here if you have a mu on the left?
Yes.
And a mu hat?
Excellent question. I'll talk about this later. So you can add sums. So sigma is my own favorite syntax for sum. Sigma 1 is left, sigma 2 is right. And then on the other hand, you would have a pattern matching with two cases. Okay, if I'm sigma 1 x1, do c1, other ones do c2. You could have pairs that are defined by projection. So that means that this is the context that says, first do the ith projection and then continue with E. And then the pattern matching on the left would be defined by with two cases. And this is the syntax for pairs that say, if you project me, I do C1. If you project me on the right, I do C2. And all of this is very nice and symmetric and natural. And it kind of helps my point that this is nice syntax for a certain definition of nice. Okay. Yes, and you can do many other data types if you want. Yes, Phil.
So the last line, sorry, the second to last line, the penultimate line, that's defining sums.
Yeah.
So what's the last line defined? Normally the dual of a sum is a pair, but you've already
Yeah,
got
it's a pair. Yes.
But you've already got pairs.
So we have two kinds of pairs. You have the pairs that are constructed by giving two terms and that are observed by matching on the two values at once. And you have the pair that is, so whose consumer is constructing by a projection, and that is defined by matching on two potential consumers. And of course, for a programmer, maybe this is the same, or maybe you could think, well, one sounds a bit more like records or lazy pairs, or maybe you know of linear logic, and you think, oh, there are the pairs of linear logic, but I don't want to get dragged down in the details too much. But yeah, so there are two reasonable syntaxes for pairs that you can have in your system.
And they have different semantics. One is strict,
Yeah.
one is lazy.
It's a bit too early to say anything about that, but at least they have different syntax and reduction rules. But you can write, with this reduction rules, you can write function to convert pairs in one side to pairs in the other side, as you would in a programming language.
Is there
Sorry, I have one more
Yeah.
question.
Yeah. Wait.
I'm slow.
You
Let me go
might
first.
get us being assigned a Phil's question budget, so be careful about that. Yeah.
So you replaced lambda x with mu x alpha.
Mm-hmm.
If I think of lambda as primitive, is mu x alpha the same as, mu x dot alpha the same as lambda x mu alpha? Or mu alpha lambda x?
Yes, I think so. But why would you think of lambda as primitive? That would be just not wrong, but let's say there are many tastes in syntax. But one thing that I think everyone could agree on is that regularity is nice. So that's why I say this syntax is nice. Maybe having lambda as a primitive is fine, but I don't know of strong reasons for it. Yes.
Just to make sure I'm reading that right.
Yeah.
Pi is a symbol, not a matter.
Yeah. So it's kind of the dual of the sigma. Yeah. Only people that know experts in this stuff are asking questions, so I'm kind of worried. Okay. So
can I just?
oh yes, Sam. Hey, go.
Is there another kind of sum as well?
You could have one, yes, by
Because the products.
yes.
There's sort of obvious duality between the bottom two lines. But
Yeah. So yes, but I won't talk about it during the
right.
Just a small remark. You might think that the syntax is nice and regular, as I said, but a bit frightening because it's more complex and unfamiliar and so on. And that would be correct. So a remark on it is, one way to think of the syntax is some of the parts of the term that we usually write are turned upside down. So this is a program where I take some module M, I project to get a function, I apply it to two arguments, returns a pair, I unpack it, and then I do T, okay? And the way you write this in the syntax that I've shown is actually closer to what I said than what was written on the first line, okay? It says, well, start with M, and then project, and then apply X and Y, and then you'll get a pair, and then you do T, okay? So here, the order of the terms on the slide does not help you think about the data pipeline, if you want. Sometimes it's nice to write in this style, but sometimes people write with pipes to be more explicit. And this style is closer, so we focus first on what's deep down inside here is outside here, okay? So that's why I mean upside down. And in particular, I can ask you a question I was asking myself recently. So suppose there is a game. So T is x1, and I tell you, give me instantiations for the three variables in this term so that the whole result is 1. Okay? Should be easy. And of course, you can solve this problem instantly because you are familiar with functional farming. My claim is that it's much easier to solve the problem by looking at this shape. Okay, so in a sense, you can solve this problem in a systematic, regular way by looking at this shape than by looking at this shape. So, okay, well, I need to find an instance for n. Okay, I don't know what it should be. Oh, but I'm done on a P1. So it should be of the form something and something else, and I only care about the left thing. oh, but then I'm applying a function, so the lapping should be lambda x, and then, oh, I'm applying the second function, so it should be lambda y, and so on. I can fill out the distance I want progressively by just reading this shape, which suggests maybe that this upside-down form is nice and in some sense more natural than what we write in natural deduction. Yes?
So the process is I take the term at the top, stick it into the empty stack, and then reduce until I get stuck. I mean, is this what?
Yes, yeah.
Because there are two different syntactic classes, right? You have a
Yes,
term and
yes. But I could also have written mu alpha and alpha here. Thank you. Okay. There is a lot of things I could say and want to say, so I'm trying not to go too slow, but not to go too fast either. Tricky business. So you know about eta expansion rules. There is a talk about making eta mainstream right now in the Haskell implementer workshop. And in this syntax, the eta rules are just beautiful. If you look at the lambda calculus syntax, well, you all know of this rule. Okay, if t is a function, is the same as the function that to x says t of x. And you might know of this rule of variance of it, which is, well, for a let on a pair, so for pairs defined by pattern matching, it's kind of ugly, okay? For any context C, if I have C and inside I have a term that is a pair, I can first unwrap the pair outside and then inside the context just tick what I got, okay? So you may know of this rule, otherwise here it is for you. And in L or in mu tilde, it's just nice. T is the same as pattern matching on the context. If you know that you are the function type, you expect that the guy against you will be a function context. And then you do T against what you just saw. And for the pair, the rule talks not about the terms, but about the context, or the coterms, if you want. A consumer of a pair is just the same as first matching on the pair, and then playing the consumer against what you saw. And all the connectives, they follow this very simple recipe, and they are just very nice. And I would say, arguably, I think it's a killer feature of mu tilde. It's one of the things that let me say with confidence that it's a nice syntax. In particular, in call by push value, I don't know.
That's the eta, yeah.
Yeah, of course, yes. But how nice does it look?
Like this?
I don't remember. Okay. Okay. I've said if t is a function, so there is a type system, of course. So this is the grammar, a subset of the grammar I've seen. And the type system, so one thing you may notice here is that there is this star construct, and I did alpha, beta, and so on here. The realization is a star, the empty stack, is just a special case of a coterm variable, or a covariable, if you want. So it's something to talk about a stack that is unknown and atomic and not named. And in practice, when I write a whole term, I will only use star, but inside I do mu alphas and so on, so there will be more variables showing up. So when I want to type check one of these things, I will use judgments of this form. Let's start with C. So the type of C will contain a type for all the variables in C. This is a type judgment. And then a type for all the covariables in C. And one way to think of this type system, or of the whole thing, is I'm describing a process that takes as input the stuff in gamma. So I have X, it's a pair, I have Y, it's a sum, and so on. And then the covariables in delta, they correspond to possible outputs. And the rule of the game is deconstruct what you have in gamma, and then incrementally you can build values that eventually you will send to one of the outputs in delta. Okay? So the judgment for the term says, suppose you have decided to work on a specific output of type A, well, you can decide to send a T there to build the data of shape A. And the judgment for the coterm says, suppose you have decided to work on a specific input that you are supposed to consume in the process of type A, then the coterm E will deconstruct this input and then continue with the computation. So the typing rule, let's start first with maybe the most central one, this one. It says, well, a machine has this type if T produces an A and E consumes the A. So you probably recognize the cut rule. Okay, so this is just a cut. then you have a rule for variables that say if you have an input of type A in your context, then you are done. You can, if one of the outputs you must produce is A, you can just say, well, X. And then you have the symmetric rules for covariables. So if you have an output that expects an alpha, and what you are currently deconstructing is of type alpha, you can say, well, my consumer is just alpha. Yes, I see. Then you have rules, of course, for the various connectives. So here, this mu tilde pairs defines a coterm that decomposes a pair A1, A2 by adding the names in the context and then continuing with C. And the constructor, the symmetric constructor, is just the pair rule that you know about, plus the delta business. The functions look as they should. So let's start with this one that is maybe easier. So when I say you match the input X and the output alpha, you literally mean that. So you get an A as an input, an extra A as X as an input of type A, and then now you get the option to finish your computation by sending a B in the input alpha. And then the stack, the continuation stack rule is one that maybe you have seen before. So T cons E, well, if T, it consumes an A to B by first producing an A, so T must better produce an A, and then feeding the A to then consume the B that you get from the function. Okay, and then there are rules for the mu alpha and mu X. And one way to think of these rules is, I was saying, okay, this judgment, you have already decided which output you want to use. I want to use an output of type A, and I will send a T there. Okay, the output is kind of unnamed here. But at some point you can say, well, okay, I worked on this output, but now I want to pause and look back at the whole thing and maybe work on something else. So let me name this output that I was working on alpha, store it in my context, and continue with an arbitrary computation. So this is one way to think from a programming perspective about this typing. Okay, so you may recognize the sequent calculus. Yes?
So, questions. So what you've said about the star business, that would be the top right rule without the alpha on the right? Top right one?
Yes?
Yeah, without the alpha on the right, that would be the star rule, right? That's what you...
So
for
star in this gamma is just one of the covariables.
So there's a specific one, so it's the same
A
way.
specific one.
Okay, and delta is a set, finite set.
Yes.
Not a list.
Yeah, I don't care.
Okay, thanks.
And so it's a type system,
Yeah.
and of course it corresponds to a logic. So if you erase the term parts and the variables and so on, you recognize that there are multiple covariables because delta can have several things in it. So it gives you classical logic. It's a sequent calculus for classical logic, with kind of this new discipline to decide where to act. It's not exactly what we do when we present the sequent calculus for the first time, but it's a sequent calculus for classical logic. So again, value judgment, it's nicer than lambda mu. If you know about lambda mu, just forget it and use mu tilde instead. And it's also nicer than primitive call CC, and you can encode call CC in a fairly natural way. You can define call CC. So call CC of f will, in a functional language, will capture the current continuation as a function k, pass k to f, and of course it's still there, so it's running in the current continuation, which is the same thing as k. Okay. So the way you do it is, okay, it's a term, so you start with a mu alpha, and then you say, okay, I have to pass an argument to f, so let's write f. And then what I write here, well, alpha is the current context, okay? So I want to write a function that takes an argument and a covariable, and will run the argument against alpha. And this is the reification of the continuation as a function. And of course, the whole thing, so I send this to f, and then I continue with alpha, which is still the current continuation. And you can notice something interesting, which is that beta here is not used, it's discarded, and alpha here is used twice, it's copied, okay? And which remember, it's not something that I came up, or the essence of classical control in this sense is a non-linearity. So, in particular, you can restrict your system to get an intuitionistic system instead of a classical system, if maybe you don't want to have call CC in your language, because as everyone knows, languaging is call CC in them. This was a joke, not a value judgment that I actually believe in. And there are two ways that are essentially the same to get an intuitionistic system from that, and they are both like very simple. You can take something that was done in classical mu tilde and look at it through the intuitionistic lens. It's very simple. The first is to say, well, I want my co-context to be linear. So in the variable case, you forbid weakening, and in the other, you use this additive context presentation. Well, I'm actually cheating. This works, but what this actually turns out to be is here you fail if you have some covariables. So in this judgment, it's not too hard to convince yourself that this must always be empty, otherwise it will not be provable. So this degrades into, this rule, which is just like linear co-context, they degrade into a system where this is empty, this has exactly one thing in delta, and this has also exactly one thing in delta. So it's linear logic in a very, very limited sense. And there is another way to present the same thing if you like syntax more than typing, which is to say, well, this business I said about having several type co-variables, forget about it. We just have star. And then you get a very weird system. It's amusing that it works. So if you look at, for example, the explanation of TU that I gave, mu alpha, you notice that, of course, the covariable is handled linearly. And so I can erase all the covariables and use star instead. So this is mu star. Star is the only possible variable in its syntactic category. TU against star. And then you get something kind of weird that if you have a term, and the right-hand side is from, if you want to write a lambda against the end of the stack, star. On the left, you start with a mu that binds star, and therefore the previous star variable is shadowed. Okay? So at any position in the term, there is only one variable that is star, and whenever you name a new variable, you forget about the previous one. And that also gives you the intuitionistic behavior. If you know about labeled logics and so on, it's kind of the same thing, but in a very kind of dumb syntactic way. So if you like classical logic, good for you, you can use mu tilde, and it's the best thing to use. If you don't, good for you, you can use mu tilde as well. So as everyone knows, computational classical logic, kind of hard, okay? And then there is the example that Michael had in mind quite a bit of slides ago. Okay, when you have a mu alpha against a mu tilde, what do? You have two choices, okay? Either you say, well, I will reduce this one, and you get this, C2, where X is replaced by, typo, it should be mu alpha C1, okay? Or you reduce this one, and you get the other thing with the dual typo. See, even typos are symmetric in any case. Okay, and there is no reason why these two comments would reach the same thing eventually. So here is an example where they both ignore their the bound variable, and on one side you do X against alpha, and the other Y against beta. You get completely different results. Different results, different outputs. So not the same thing at all. You have a calculus where completely different terms are equated by the reduction relation, which sounds bad, and it is. It's trivial in this sense of trivial, so you don't want to use that. What did I say? Yes. A remark: if you add the intuitionistic restriction, actually eventually you get confluence in the end if you are in a normalizing system, but for kind of reasons that do not come from the calculus but just from intuitionistic logic. So one way to solve this critical pair is to make a choice. Okay? If you always decide to reduce the term, to reduce the mu alpha first, you get call by value evaluation, and if you always decide to reduce the mu tilde first, you get call by name evaluation. Kind of cool. Yes?
Wait, but the abstract machine you started with was call by name.
Yes.
So how would we suddenly become call by value?
Well, I claim that if you just keep adding this stuff, and then you say, in this case, you don't do the call by name thing, then the behavior of the whole machine will be exactly call by value. Magic. I have maybe a longer explanation, kind of example. I think it's an example. Oh, no, it's not an example. It's so what do I mean by prefer reducing the term or the content? How do you represent that in your calculus instead of saying, well, one thing you could say is to say, when you see this, always reduce it this way, but then you have two rules with a priority between them. It's kind of not nice. So there is a common way that has been used, the usual trick. When we want to restrict reduction, we say, well, you are only allowed to reduce values, for example. So not any term, but just when it's a value. So here we can do it if we want to get, for example, the call by value solution. So this is the syntax we started from. And then what I say, well, I want to reduce I want to reduce the mu tilde first. Okay? So, no, sorry. That's all. If I want to reduce the mu alpha first, one way I can do it is by saying, this rule, you are only allowed to do the reduction if you have a value here. And then find out a definition of values that does not include mu alpha. So very simple. How do I do it? Well, I split terms in two categories, terms that have mu alphas and values which have the rest. Okay? And you get call by value. And you can do the symmetric thing. If you want to prefer reducing on the right, you do the, and here you have a definition of co-values, and this is called by name. Okay? So you have a system that is ill-behaved because it's too general, and there are two there are two choices that sound arbitrary, but they give you things that are well known and interesting on their own. Okay. Pointers. So this was mu tilde. Yes. Question.
So does this roughly correspond to, if you have the law of the excluded middle, choosing whether to first say, I think A is true, or whether to first say, I think not A is true? And then, change your mind later.
So I don't know. And I think it would be, I would need to think too long to answer given my typology. You can write the excluded middle rule in mu tilde as an exercise and look at whether it sounds like what you are saying is true. So yes, do it yourself. Pointers on mu tilde. So mu tilde is not really the thing I wanted to talk about, but the basic thing that not everyone knows and should be taught first. So I think, but the experts in the room may correct me, that the main ideas in mu tilde were put together, they were existing independently, by Pierre-Louis Curien and Hugo Herbelin in 2000, okay, with their paper, The Duality of Computation. They introduced the syntax, mu tilde, but just like Phil, they had lambda as a primitive, and just as Phil, it was not the best choice they could have made, but it's okay. It's okay. Then there is a very nice tutorial paper by Paul Downing and Zina Ariola, just this year, fresh, hot from the press, on, so it's called Tutorial on Computational Classical Logic and the Segment Calculus, so it's nice. There are two criticisms that you can make. I'm looking at the camera, so then they can watch the video. First, they don't talk about the intuitionistic restriction. It's very simple and kind of nice. They should have. And the other is published in JFP, which is an ugly closed access journal. And you should never use JFP and always use logical methods in computer science, LMCS instead, which is nice. Open access publishes paper on archive. Yeah, don't use GFP. And don't send special issues about effect handlers or whatever.
You can't submit to the archive before you submit to GFP. And then it's
okay, I've shown you some syntax here. Maybe you have not been inspired to use it yourself in your work, but I can convince you by giving you examples of excellent people that did this, were inspired by mu tilde. So one example are the copatterns of Andreas Abel, Brigitte Klenka, David Thibaudot, and Anton Tetzer. I mean, there were several papers on copatterns, but this is, I think it's the first one. Not sure. I think yes. Another, so it's kind of talking about co-induction in a nice way with co-patterns, which are a way to define records and lazy structures, which is nice. Another is the work by Paul and co-authors. Structures for structural recursion is also about co-injection. So the idea is, when we talk about recursion, there is this notion of structural recursion where you structurally decrease on the argument. Okay? And actually, you can present co-injection in the exact same way by saying co-recursion can be structurally decreasing on the co-argument, on the co-term. Quite nice. Okay, so then there is work by Etienne on classical sequence calculus with dependent types, which is something that we didn't really know how to do. I think before this paper, and it's kind of doubled down on adding, the kind of things they do, some form of the axiom of choice and infinite lazy string, because why not, and so on, in further leaked publication this year. And then there is work I did on equivalence with sums and the empty type. You couldn't tell from the paper that it's using mu tilde, because the paper is not, but I was in my head, and then I was a bit worried that reviewers would say, what's this syntax we don't know about? So first I wrote the paper, and then I write a tutorial for the next paper. Okay, so now I can get into the heart of the matter. Maybe we have some questions on mu tilde before. Some more questions? No? Yes?
I think the answer is yes, but can you also write shift and reset in mu tilde?
So I think not with just the mu tilde I've shown. So it's not the only, so for example, if you were an expert by about call by need, you would ask me about call by need, and you would need a different strategy. For shift and reset, there has been work on delimited control on top of mu tilde, for example, in Guillaume's PhD thesis, but it is using an extra syntax with this. So basically, you have a dynamically bound, you have dynamic binding for one co-variable and a stack on. So you need to extend the machine a bit. But so also in this example, it's an ID, it's a recipe. It's a family of systems that you can extend to make your own to add more things. But the syntax, as I've shown, does not let you express, I think, delimited control directly. So let's go into polarity, just a bit, so kind of open. Yes?
So my system in call by value is dual to call
Yes.
by name. Again, basically, I got rid of lambda as a primitive. I had and or as primitives.
Yes.
Is that a subset of this with one of the two products?
So this is, so I think that the two systems are equivalent in the classical case. You could probably define negation from lambda or use product and negation as primitives to get lambda. In this case, I would recommend rather using product and negation as primitives, which is what you did, which is nice. But then the intuitionistic restriction is harder to define because you have to remove these parallel pairs and this negation and so on.
So I have negation as primitive, and you have this mu with the dolphin.
Yeah. So I was making my life easier because I live mostly in the intuitionistic world most of the time, so I see it from. But so
okay, so I wonder what the trade-offs are there, but we'll leave that offline.
So I've talked about how you can restrict the system to be confluent again, and in particular have an equational theory that is not trivial. Yes.
So, for the previous session,
Yeah.
you mentioned how this makes control-wise, you didn't quite mention the relation to CS, or maybe we missed that? Or how is it, since there are similarities with CS, how is this?
One way to think of it is that you can factor a CPS translation by first going into mu tilde and then going back to the lambda calculus. And when you go back to the lambda calculus, mostly you erase distinctions that you made. I'm not making any value judgment. I'm letting you make your own. No, I like CPS, of course. So this one is called by value. Okay, as a global restriction, I say every time there is this pair, you go on the left first. There is another way to solve this confluence problem, which is arguably more interesting, which is to use a type-directed solution. Of course, at ICFP, people would say, yes. Okay, let's look at types and split them into categories. Let's be divisive. Say there are positive types and there are negative types. And so this is a particular example of a family of, so for type variables, I don't know, so let's annotate them with a polarity. So there are many choices you can make, okay, but this is one of them. And then pairs, the ones that are defined by pattern matching, they say they are positives, sums positive, functions negative. The pairs that are defined by projection, let's say they are negative as well. I mean, let's say, no, I know why I say that. And then add any stuff you want, bring your own polarized connective. And then in the end, I add shifts. So I say, well, okay, actually, because we want to be divisive but not too much, let's let you use positive, so positive type inside the negative or the other way around. So for example, here, notice that the pairs, I ask for the two components to be positive as well. Maybe you actually want to do a pair of functions. And if you want to do a pair of functions, you do a pair of shifted negative types, which are functions. And notice the function, you have a positive on the left, a negative on the right. This is all very cool. Okay, so you add. Some people don't have shifts, and they allow pairs to be any type, A, B, which is either a P or an N. Okay, many choices, and here I don't know if there is an arguably better choice. Also, the shifts, you can actually encode them. So the positive shift, if you don't restrict polarity here, you can say the positive shift is 1 times N, and the negative shifts, and so on. So there are many ways to go at it, but this is one of them. It's fine.
So
yes?
Why are you saying types are not a global solution? Or types are a global solution?
Okay, it's a global solution along a different plane of existence. And then I'm going to say, okay, the negative terms, I want a reduction system in which the negative terms, they are inert. They don't reduce. Basically, they are values. Okay? And the positive coterms, same thing. They're not interesting. They are just values. And the interesting stuff will happen with the positive terms and the negative coterms. Okay, so once I made this choice, I can refine my configurations. There are two. So now I'm assuming for the rest of the talk that the machines I write are well typed in a typing judgment that looks very much like the one I had before, but with some more polarity in it. Okay? And so when I have a well typed configuration, I know that it's a cut. So the two sides are cutting on the same formula, the same time. So they have the same polarity. So there are two cases. There is the one where it's a cut of two things of negative polarity, or a cut of two things of positive polarity. And when I'm cutting on things of negative polarity, I know that the term is a value, so I can write V. And negative polarity, I know that it's a co-value, I can write S. S is for stack. Okay. And then in the terms, and then again with the coterms, before I had mu, which was not a value, and everything else which was a value. And now I can actually distinguish two kinds of mu's. There is the positive mu and the negative mu. So you can think of it, the syntax being just mu, but because I'm thinking of the typing derivation, I write a plus or a minus to help you in your mind think about the polarity without seeing the type derivation. Okay? So if I have a negative mu, it is a value because all negatives terms are values. Okay? So I can add back a restricted form of mu here, and then only the positive mu's are not values. And the rest is almost as before, except here, and I will talk about it later. And same thing with the coterms. I have a positive and a negative mu tilde, and now the positive mu tilde is a value, and the negative one is not a value. Okay, so this sounds like very, I mean, I explain my design choice here, and the rest is kind of automatically derived from it. And then I can define a reduction. It's essentially the same. I plan to say first, it's the same as before, just polarized, but I thought I could show the rules because I was very pedagogic, didactic. So this is the unpolarized rules of the system. This is the syntax of the polarized system. And these are the reduction rules. And you can notice that they are exactly the same as before, except that all the substitutions are by value or by co-value. So I only reduce, I only do substitution when I have a stack, a co-value. I only do mu tilde substitution when I have a value. The pairs I expect that have two values, and so on and so forth. And then there is maybe slight subtlety. In the syntax here, I've written mu plus and mu minus, and here I have a single rule, but it's the same rules that applies to both. Okay? So if I have mu plus, so the thing on the right is a positive coterm, so I know it's a stack. It's always a stack. But if I have a mu minus, the thing on the right may or may not be a stack, co-value. So writing S here is a restriction on the reduction. Okay. In the negative case, this means that I will restrict the kind of things I let you substitute on the right. So this is a call by value, co-value evaluation order directed by the types. Just a comment here. Here, instead of writing TU as before, or here TE, I have these values and co-values. Yes, in yellow. I wasn't sure I could use my finger during the talk. So then it raises a question, what about TU or stuff I could write before? Yes?
In your syntax for C, you have two kinds of command, right?
Yeah.
But this plus and minus doesn't appear in the syntax when you write.
So there are two ways to think of it. One is to say the plus or minus is here to help you. It's not in the syntax, just in the type derivation. And the other is to say I'm lousy and I write this. For example, here I know it's a plus because it's a cut on a pair, so I don't write it because obviously it's a plus. And here it can be either a plus or a minus, and I want both cases to hold. Yes?
So if I heard you right,
Yeah.
that rule with an S in it on the bottom, the reduction for mu,
Yeah?
that S isn't actually always an S?
No, it has to be a co-value, always. You're only allowed to reduce when you have a co-value here. So depending on the return type of the function, this may be a restriction or not. Okay, okay. Moving on. So here,
if it's a minus,
maybe you want to write TU where T and U may not be values. Okay, so how do you do? And there are two design options you can do as a designer of your favorite polarized system. Either you say, well, the user has to write an explicit evaluation order between TU. So I will not let them write TU. They have to write, for example, this instead, T, and then you get X, which is a value, and then you can write this, if T was not a value. Or same thing for the cons. Or you can, if you are kind of a more permissive person, you can add reduction rules in your system. When they see something that is not a value, they decompose it automatically. So these are the zeta rule, and I think they were introduced by Phil, or at least presented in an engaging enough way, whatever. Well, there's zeta rule, and so one possible rule you could do, for example, is to say, when you have this and T is not a value, you reduce to first reduce T, and then you do this, and now you have a value here. But then this rule, sometimes if I could have a rule that would split both members of the pair at once, and then I would be choosing an evaluation order. So maybe adding this rule adds some decisions in the system about how to evaluate it. Okay? Okay. So what I was going to say here is that, okay, I have to speed up just a bit. So when you write the syntax for TU, the same syntax, depending on whether the polarity of U is negative or positive, will give you a call by name or call by value function, in the sense that the argument will be first before it's passed to the function or by the function itself. Okay? And this comes from the polarized rule that I've shown. Summary, so we say L for any of the polarized mu-tilde that you like. It's a type-directed relationship of class, the non-confluence that occurs. It lets you mix call by value and call by name locally in the system. So because we have this shift, you can kind of, you take a term, you annotate it with the polarities, and say, I want this to be positive, this to be negative, and with the shift, this is not a restriction on what we write. And then these polarities will direct some part of the program may be called by name, some other may be called by value, and so on. So it's kind of fine-grained. And you can make a border claim, the computational interpretation of classical logic. I said before that lambda mu bad, so I killed one of my competitors. Okay, so kind of cool, kind of cool. And it's constructive. Sometimes Bob Harper says that, you know, classical logic is not constructive, and he's not always right. And I think it was his first thrift yesterday, so have a happy first thrift, Bob. And the best pointer I know about these polarized systems is Guillaume's PhD thesis, and he has written papers, so do others, about the system if you want to know more. I have 5 minutes left, so quickly, an example of effects. Okay. So, suppose I have a set of output literals in a set O. I can define an operator on sets, okay? T of x, which is a list of O's and a pair and an x. And then I can extend my syntax of command with a primitive print effects that take an O, okay? And I can give a definition of what print means by saying, well, print O.C will return the pair of the singleton list O and C. So instead of reducing to a command, I reduce to a T of a command, where commands is a syntactic set, you know, of terms configurations. And then, yes, okay, there are rules about how to compose these things, you know, these T operators that have a special shape. So you can define it in such a way that if you print 1 and then 2, you end up with a list of 1 and 2. And you can do the same with many other kind of simple effects. So state, you can do it this way, you can add get and set, and you can add partiality as well in the same business. So basically the idea is one way to add effects to Matilda, which we are experimented with, I'm not saying it's the only ever way, is to add the effect operations at the level of commands, and to add the semantics of the effect to the semantics of the operation. And effects and polarity behave, they mix together as they should. Okay? So if you write this following Ocaml program, print 1 and then return the pair x, y, you want to turn it into Matilda, you get this. Okay? This is returns a pair, so it's a positive, so you start with a mu plus alpha, print 1, and then you do this. And so this is not a value, it's the mu plus, so it will reduce when you put it against something, and it will print first, and then return the pair. If you do print 1, and then you return a function, okay, then you get a minus, because the function has a negative type, and this is a value. So the effect here, although the print is outside the lambda, the effect will only be performed when you actually pass an argument to the function, and each time. So this corresponds exactly to if you extend Haskell with side effects, and you disable all the crazy stuff, this is what you would notice. So it's a kind of call by name effects, and it's kind of hard to work with. But and this is what makes this anti-expansion rule that I talk about still work nicely in a system with the effects. So people usually they say, you know, you need to restrict your eta rule to be only eta on values and so on when you have effects. And here these rules, polarity and effects, the same rule as before, they do this. They behave in the right way. So what do I keep? Yes, we had the right eta law. The symmetry of purity, so you can define a notion of, I'm done, I should stop now, that's right?
It's about time, yes.
Yes, okay. So, okay, so let me switch to, so you can define notion of purity, so there are dual notion of pure on both sides, okay? Pure and co-pure, we call them linear. So pure terms are pure terms. Pure coterms are actually strict functions, surprise, surprise. This and you go, and interesting, and I was planning to do some category theory, so I will not end up doing any category theory, except to give you with this bewildering slide saying, okay, the shifts, there are two adjunctions about it, and sometimes when people say the up arrow is an adjoint of the right arrow, they mean it in one sense or the other, and actually there are two, and I also change the notation in between, because they correspond to one adjunction about pure functions, and one adjunction about effectful object in a polarized reduction, so it's kind of cool. And I'm done. Yes, L polarized version. Hopefully we will write this tutorial actually someday very soon, and it's a good syntax to do many things. Thank you.
Okay, thanks, Gabriel. I think, well, there's been plenty of questions during the talk, but if someone wants to ask another one?
Can we ask someone not Phil? Not personal.
It's going to be a very nice question. We'd like it.
Okay, okay. So I will ask you what your question is right after the talk. Go for it.
If you look at Gerard's point of view on intuitionistic versus classical logic, he points out that the main difference is that you can do contraction and weakening only on the left side, only on the context side. You are clearly going for symmetry. So how you didn't talk too much about structural rules. So are they symmetric, or how far you could go with symmetry with those?
So Scherer is an appropriate person to cite in this presentation. He had a paper called, you know, A New Constructive Logic, Classical Logic, which was way before this work existed, but had some of the same ideas in it. So I did make the point that you can go from the classical system to the linear system by restricting the structural rules on the right, by asking for the system on the right to be linear, the connectives to be additive, and so on. So indeed, what you say is correct, and you can see it in this system. If you force the right context to be linear, you get back intuitionistic logic, which does not work in all presentation of the sequence calculus. It happens to work in this one, but sometimes you can get beaten by the application rule, the left application rule. You can also look at what you get if you restrict the left context to be linear, or to have only one thing on the left and then several things on the right. There is a paper by Thomas Erhardt on the stack calculus that has this property. Many people have done interesting things with that. And then there is even more categorical things that you can do. So you start with a very simple kind of linear on both sides system, and then you enrich it. On the left, you get resources. On the right, you get control effects. And if you mix both, you get a system that has plenty of weird behaviors. So, but I'm not the most appropriate person to talk about.
Let me ask my question. Where are your slides?
They will be on my website tomorrow.
Thank you.
And we can put them up also on the conference website if Gabriel is happy with that. So,
Every time I give a talk, I try to remember to put the slides on my website.
Okay,
thank you.
Let's thank Gabriel again.
And thanks Ohad for his computer, which was instrumental in giving me this talk.
We should thank the
And we have 10 minutes before the next talk, so if anyone